and he's going to tell us about some applications of SOMs and optical trapping and various other kinds of things.
Great, yeah. So thanks to, I wouldn't say organizers, because Ranjini and Ronojoy have been known to me for the last, I think, 17 years or something. Just makes you feel really old also anyway. So it's interesting because Ranjini is exactly 1 year senior to me and I'm 1 year senior to Ronojoy, so we form a nice chain there. And of course it's fantastic to come back to Bangalore because I spent 13 years of my life here, and especially this room itself occupies a very special place because I've heard absolute stalwarts of physics speak here, Cohen Tanuji and Michael Berry and all that, and standing here and speaking is quite a thing. It's really hallowed place, and thanks for giving me that opportunity at least. So yeah, so I'm going to talk about microbubbles in tweezers, and this is again somewhat but I sort of take off from where Shomojit stopped, and I must say that I loved his comment that all human beings are liquids, which is really nice, and especially keeping in mind the amount of liquids we have been having for the last 2 days, it's really more pertinent. We are all liquids. So anyway, so we are actually going to talk about this way we use this liquid metals or soft metals as he calls it, soft oxometalates, which is quite a tongue twister. And that is basically, again, so I am the physicist, of course, not a materials person, and my training, for those who know me, has absolutely been not on soft matter or anything to do with material science. I've been in optics and atomic physics, basically using optics for atomic spectroscopy, and now I've moved on to do things that are absolutely alien to me. So what I'm basically learning continuously for the last 5-6 years. So I realize more and more that I'm such a complete novice in these things, but fortunately I've had very good people, both students and especially collaborators around me, who have helped me learn. And what I'm going to share with you is a part of that learning, what we have acquired for the last about, I would say, 3 years. And that has happened again because we have had a very good conglomeration of competences around us, because had Shomojit not given me the materials, I would not have been able to make these bubbles and all. And of course, the materials, the things that we did would not have been possible with just the materials, obviously, without, the trapping part comes because of the physics. Yeah, so this is what we are. It's called the Light Matter Lab, though we concentrate principally on more of the, the mesoscopic matter, because, during my PhD time and all, I used to work with atomic gases. Now it's more like solids, but very small, mesoscopic solids, I mean microparticles. Nano we have not gone into so much, but and what you see here is what we achieved in the lab. This is IISER written with the help of bubbles mediated by SOMs, and this is the group. This is my first PhD student who is in Germany now. He's recently won the Humboldt scholarship, and these two were the first students that joined the lab, MS students, and they were the ones who really set up the lab. And both of them, this is in IISc, he's with, I think, Vijay Shenoy. Shomit is in Singapore. And these two and myself, and then Basudev came in, we set up the whole thing. And Shudipta is my current PhD student. Shubhajit, Shubhra, both are here. They, of course, missed the train. Fantastic achievement while coming here. Ratnesh, Orgo just finished their MS. And these two again finished their MS. I should have put them in red. They're still there, that's why I forget putting them in red. And of course, this is very crucial because in the IISER system, you have this continuous streaming in of absolutely motivated kids coming from for example, Ratnesh was in my lab from his second year or first year, summer. He spent from that, I think we have had like 6 years almost now together. And the amount of learning that develops with people who are continuously coming with you is really very useful. And the collaborators, you can see, it's a new field for me, and I learn from all these people. Ronojoy, of course, now has almost become the theoretical mentor, I mean, not theoretical mentor for the theory side, I would say, for my students in the soft matter things that we do. Shomo, of course, together we have done a lot of very interesting things. Shubhashish Dattagupta is, he's a very senior person in Hyderabad, and we're writing a book with him, actually. We've almost finished. It's coming out next month. It's basically on, it's basic optics. And Partho and Taposh, the biology work we've just started. And so this is a brief overview of what we do, because We are basically, we work on almost, well, saying all aspects is probably a bit too much, but we work on as diverse aspects of optical tweezers that can be thought of probably, because mostly optical tweezers are thought of as tools where you take things and move them about and cut them and do whatever you want with them, as Prerna was also saying that you can do a lot of very interesting applications with them. But in that process, a lot of very basic stuff has been overlooked, and that is what we have. Even some instrumentation part we have developed, of course, which is absolutely essential, and we were lucky that even that instrumentation turned out to be useful enough to merit publication. But this is, for example, something which we really kind of found out in tweezers, where just the very, very tight focusing of light which you achieve during optical tweezers reveal some extremely exotic properties which are not manifest in light when it is either propagating with collimated light, or when it is focused weakly by lenses. But essentially the degeneracy between polarization and trajectory gets removed, and you get some extremely interesting things which you can actually use to manipulate microparticles. I'm not going to talk on that today, but this is again something which we are developing nicely now with mostly with Ronojoy's help. We are doing this kind of time domain analysis of particles, which gives you a very nice look into all kinds of interesting information about the trapping environment, and also things like what happens if you achieve motion that is not diffusive, which is like sub or super, which happens so much with bacteria or active particles and all that. So some time domain analysis that we are developing, Bayesian statistics. This is something, of course, we've probably seen the poster that Shubhajit has put up downstairs, where we are looking at, that is the very basic thing of hydrodynamic interactions that we have looked at, where you just have a coupled pendulum inside a liquid, which basically has some very interesting applications. And we, by the way, figured out that viscosity indeed is a very important parameter, and the resonance shifts a lot. That was a mistake which Shubhajit did, which we actually rectified yesterday night. So this is the part that I'm going to talk about a lot today, and some very interesting things with bubbles, which is actually, well, Shomo has spoiled half of my talk, but still whatever I've recovered of that, I will say a bit. But mostly after that, I will be talking about bubbles in the sense of how they can be used as this very nice flow probes, and how they can actually manipulate particles by doing funny things to the flow. So this is something, again, we have started very recently, DNA protein, where we are actually being able to pull proteins and look at their elasticity, and we have sort of, it's very preliminary stage, but we indeed have kind of at least theoretically matched the elasticity values of a protein when it is just pulled by tweezers. And we think we have a kind of a new approach for doing this force clamp measurements, but I'm not going to talk about that today again. So basically, yeah, so transients, my talk is transient. So why is transient so important? So what you see here, anybody know, Bengalis know this, but I don't know if others know. So this is basically the Durga Puja that happens in Kolkata. And I remember when I was in IIT Guwahati once for a Circ school, there was this very senior professor, I think he was from Punjab, and he was manifestly, he showed his complete surprise, utter surprise, that why do bongs indulge in a festival which worth crores? It's a huge business. Everybody goes mad in Kolkata for the 4 days that it happens. And then this happens, basically, where you just throw away the idol, right? You just immerse it, finished, it's gone, kaput. You throw it into the river. What is the meaning of all this? In 5 days, it is finished. Why so much of thing? But of course, people who know Durga Puja realize that if it went on for a long time, then the whole magic would be lost. The whole magic of Durga Puja is that it happens for 5 days. And for those 5 days, at least when we were small, we used to look out for the whole year for those 5 days to come. And then, yeah, that is the whole magic. I mean, Bengali, of course, now it's not really a religious thing, it's more like a cultural occasion. But the whole fun with it is the transience, those 5 days. That is the fun. That is not the, the lack of whatever prudence or whatever, lack of maturity or being practical. The same is with bubbles. So what you see here is a bubble and it disappears, right? So it disappears because I switched off the laser, right? But while it is there, of course, it does some very beautiful things. You cannot see here well, but this guy actually has some nanoparticles on it. And as I shut the bubble away, those nanoparticles nicely deposited. Okay, so here comes that is the mystery behind the title, the magic of transients. So basic optical tweezers, I just want some 30 seconds on it. But so basically, you know that you have a trap means it's a kind of a confining potential. You have a beam which is tightly focused. It's Gaussian. It has an intensity distribution. If you focus tightly, so this is the ray picture. So you know light gives momentum. So the intensity here is higher. If you have a particle whose refractive index is higher than the ambient or the liquid that surrounds it, it's very difficult to trap particles in air because the particle kinetic energy is much higher. So the rays will bend this way, this ray will bend this way, but then the intensity is much higher. You can think that there are many more rays here. Now the light sort of is bent by the sphere this way. So the sphere, the sphere bends the light this way, right? So the light will push the sphere that way, Newton's third law. And the same thing happens when the sphere is that way, there. Okay, so essentially the sphere basically gets trapped in the center. If you want to look at the dipole picture, you consider the minus d dot E is the interaction energy. So you know the thing will have the lowest energy at the place where the E is maximum. Very easy to understand, minus d dot E. That, however, does not work. Oh, this is my trap, by the way. So this is one of the traps. Now we have several traps. So this was the first trap. It was based on a Zeiss microscope, which is a beast, and we put in laser beams through this is the back port through which we put the laser beam, trapping beam, 1064. There are mirrors here and the objective lens which focuses it on the sample stage, and we take out, the camera is here, or we take out backscattered light which does the detection. Okay, but the important thing for bubbles now, they cannot be normally trapped. And why? The reason is that a bubble has air inside it which has a lower refractive index than the ambient. As a result, the bubble would be sort of anti-trapped, right? The bubble would try to go away to a place where the intensity is minimum, and therefore it will run away, right? So you cannot use a normal Gaussian beam to trap bubbles in the usual intensity gradient process. No, it cannot. You can use Holy beams. You can have beams with a hole in the center, like vortex beams or whatever. Bubble sits in the hole or the dark spot. We have another way of trapping bubbles, right? And that is first part of the talk. So this is the sample chamber, which is very crucial because we have this objective. This is a very makeshift kind of an arrangement that we always use. It's very simple. That's why I chose to do this thing. This thing is so much simpler than what I used to do in my PhD. That's ion trapping, far more simpler, but it yields very rich physics. So you have a you have a very thin cover slip, and you have some sample inside. You have a top slide, microscope slide, which is thicker. You don't really bother about it, but it gives you support, and at times it does help in back reflections and all. I'm not coming to that, but for the bubble it is actually important, very important. So you have the solution, your sample, which is essentially, for our case, it is something in either solution or dispersion with water, mostly dispersion with water. So for example, here it is the SOM clusters which Shomo provides us, and the laser comes in, of course, to this. We typically focus it on this top slide for this particular case. Of course, typically particles will be trapped in the solution. The thing that we do here, this is of crucial importance. And that is what I'm going to talk about. That is the controlled lithography, right? So what happens there? This is an old slide, but I'm going to be a bit more detailed than what Shomujit has said. So I'm going to explain exactly what happens. How do we trap those bubbles? So this is actually, as we said, it is not possible to trap bubbles by using the intensity gradient of Gaussian beams. We use instead something that is thermally driven, which is something like a flow sort of control. You know, the flow of water around the bubble that sets in essentially prevents the bubble to escape from the laser spot. So what happens? Initially, we start with some dispersion of SOMs, which is saturated. Lots of SOMs are around, right? So obviously, some will adsorb on the top slide, right? Some would just get normally adsorbed. What we do is we just take the laser and search for those adsorbed SOMs. And how do we search? Basically, when the laser hits, remember it's a very tightly focused laser beam, almost like less than a micron focal spot, which gives you huge intensity. 100 megawatts per centimeter square, huge intensity. And these SOMs, because of this ligand metal transition, goes to this excited state. They absorb, So when my laser hits the SOMs, they absorb, and the temperature gets even higher than what it is when I just hit the top slide, right? As a result of this very, very sudden increase of temperature, we have something called homogeneous nucleation. I'm going to come to that in my next part, but we form a bubble. Essentially, I form a bubble. And the moment I form a bubble, that is here, the bubble has a temperature that is high here and low here, right? Because this is the only part that is really hot. Thus, there's a surface tension gradient. You have Gibbs-Marangoni flow. Particles start coming in here. This is the bubble growing. Particles start assembling, coming in of their own. The convection current pushes them. So it's like you have in the radial direction it's coming in, axial it moves out. That is how it should go. But it cannot move here because we have a boundary. We have the top slide, right? So it essentially comes and accumulates at the corners, right? And then something happens which is providential, without which we could not have this method to work. Those SOMs sit there. Most likely they get melted because they are very close to this hotspot wherever we are, and they probably melt. What happens after that is you have this kind of accumulated SOMs which are probably molten, and then I move my laser spot. So then I find a new hotspot, right? Because I've already those accumulated SOMs there. So now obviously I can either have a new bubble, or this bubble can move. Energy considerations, this has lower energy value, cost, right, of this bubble moving. You can, in fact, if I don't go by that argument, just by the flows themselves, you will have a convective flow which will basically push the bubble, right? And the new bubble basically moves. And when it moves, it just has a new series of accumulation that is happening. Now this providential thing that we were saying is, or whatever, it's not providential, it's physical completely. As I move the SOM, as this heat flux or whatever is suddenly moved, there is a quenching effect, and these SOMs essentially harden, and we believe it forms crystals, and which sticks to the surface, which is extremely crucial. It makes these hard layers of possibly polycrystalline material which sticks. And then when I move my laser, I find another hotspot. Again the same process comes. I keep on moving. I essentially write with my laser, writing. My laser is a pencil now. And I basically write things like IISER or whatever, right? And the good thing is this whole pattern remains, and remains for months, okay? And that is what we finally achieve. Where is it not moving? Yeah, so this is like a little video. Yeah, so this is what my student Shubhra Kohli has done. So you can see that this is the laser going. I'm moving my sample chamber here. I'm moving my sample chamber here. And this is the bubble which is kind of progressing, right? This is the sample chamber moving. Should I play it again? I think it's good enough. So what you see here basically, this is the bubble moving again. You can see like a jet plane wake. You know what you have, those those frozen sort of gases that you have in the wake of a jet plane. Similar kind of tracks that you see, right? Like the trails of a jet plane, same kind of thing. And why is that? Because the material accumulation is happening at the edges of the bubble. So what you basically have for a static bubble is a ring like this, and that ring is essentially tracing the base of the bubble, the cross section of that. And if I have a larger bubble, I have a larger ring, right? So what you have is like concomitant rings. You have continuous and contiguous rings which just come together and form a pattern. And how do those patterns look like? This. So this is this is not TM, sorry, this is SEM image. This is an EDAX image of a SOM trail, and this is how it looks like. So it looks pretty dirty. I mean, it's like not so much of microscopic order is present, but we believe there is some crystalline order, polycrystalline order possibly, because when we do a TM, as I'm going to come through, we see diffraction spots. We actually see diffraction spots, right? So these are the patterns that we made. This is again something Shomo showed, but what I would like to emphasize here is this technique, it should in principle be independent of the material, because the only thing I am using of the material is the fact that it absorbs and it forms a bubble. Anything we have worked with carbon nanotubes, we have worked with lot of things which also absorb, which absolutely form a bubble, which come and accumulate. But the second thing that is crucial for this pattern to be permanent is that phase transition or whatever, whether things should stick. That does not happen with, for example, CNTs. CNTs nicely come, assemble, I move the bubble nicely moves, the CNTs just wash away. But fortunately, if I mix CNTs with the SOMs, beautifully they form a pattern. As we have seen in this case, this is a dye. This is a dye, Perylene, which is absorbing at 488, so there's no question of something happening at 1064. But the moment I mix it with SOMs, I see that indeed they do pattern, they co-pattern with SOMs, and when I irradiate with 532, you see green, right? This is something actually, this is glycine, this is something which we did without SOMs, just as a proof of principle. Glycine has some tail of absorption, and we saw that we could indeed pattern this. So now if I get a laser which is like continuous over wavelengths, then the thought is most likely we would be able to pattern anything. Of course, the second criteria, that is that the thing has to stick, that you either need to, you probably can design some kind of substrate where these things can stick, or you of course choose a material, that's we have to think about that, how you can get anything to, Amorish.
Is there a material that you can use to not deposit but instead etch? So can you etch?
Absolutely. See, this is something which is, the material will just assemble, it has to self-assemble because of the flow.
But let's say you have a thin film, can you etch out a pattern in that?
I think so. If you give me something which is an etching thing, it should, because see, what I am doing is basically forming the bubble, and I am pulling in the material, and I am moving the bubble, the material will just go on. So this is a very nice thing. Of course, I feel it should be able to etch. See, and the good thing about this whole technique is, see, this is basically something like photolithography. And if you think of photolithography per se, it is a beast of a process, right? It's a multi-crore kind of a thing which takes hours. Of course, I'm not going to compare this in terms of throughput and all. You can get thousands of patterns in one shot there. But suppose I tell you that I can make the mask out of this. I can probably, and this takes minutes. This takes minutes. I mean, this thing costs, well, most of the patterning that we did later on was with the 80,000 rupee microscope, an Indian microscope. It needs nothing, right? The only thing is that you create a bubble will remain trapped, and then you have to get in this material which will assemble. And then it has to melt and deposit. That is the important part. Okay. So after that, right. So pattern width, it's quite obvious. The bubble size, basically the bubble size. How you control the bubble size, and that is like you have higher laser power. For the same amount of time with a lower laser power, you create a smaller bubble, right? If you have a large deposition concentration of SOMs, then for the same amount of time you had a big bubble. So basically everything is related to the bubble size and the speed at which I sort of draw the bubble. I sort of manipulate the bubble. If I do it very fast, material does not have time to accumulate, I can get very thin trails. And of course the wavelength of the laser, because at the moment I am diffraction limited. 1064, which means the spot is lambda by 2Na, which is about 600 nanometer. The best we have ever got, steady patterns, is I think about 3 microns. But of course if I have a material which is absorbing at say 400 or 500, I should be able to get nano patterns. It should be done, right?
So you get double line everywhere.
Yeah, double line is because of the bubble base, right? Two sides of that, right? But then in principle, Pramod, we can actually fill it up also, which my student has done. So you have this double line, then you start with another bubble and just draw in the center. So you can actually fill up the whole thing, right? Okay, so these are the images again. So this is an AFM image. This is the one that I would like to draw your attention to. This is a TM image where we actually see these lattice spots, which tell us that there is some crystalline thing that has happened. This is probably a crystal. Okay, so this is the Raman transition. Shomo spoke about that. What is interesting again is that this is the AFM of the Z direction. You can see that accumulation is really on the sides, and this middle is almost nothing, right? So this is a paper. This is another paper. Catalysis, I don't think I'll go on too much because Shomo spoke about it. What we saw was, we had this benzaldehyde to benzoic acid reaction. We saw that only on the pattern we saw the reaction happening. Other than that, there was nothing. So this is site-specific catalysis, very nice sounding name. This is the thing that is cool actually. We are actually making circuits. So we have taken this conducting polymer. We took two of them actually, pyrrole and aniline. Both of them, when they are in their organic state, they are not conducting. Absolutely not. They are insulators, right? But when they actually polymerize, then starts their conductivity. So what we have seen, that is really something which we like, is that We start with normal pyrrole and aniline, but when we pattern them with the SOMs, we actually get polypyrrole happening. In situ we produce polypyrrole and polyaniline also, and then it's like an automated process. You have the thing formed and you pull it, the tracks also get formed, right? So why it happens, this is again Shomo's field, but I am going to take a shot at it. Pardon me for all my inaccuracies. So basically what I believe is that, what he tells me is that the SOMs go to an excited state because of the laser absorption, and that is at MO6 star or something. Then they get reduced, leave an electron. Electron gives rise to a pyrrole radical. That radical reacts with a pyrrole molecule to form a dimer. Now this dimer forms a trimer, that forms a tetramer, finally N-mer or whatever, polymer, right? Same with aniline. And this is how they look like. What is interesting is, if you remember the color, of course I should have had a thing of the SOMs also with this, but they are definitely, the contrast is different. The SOMs looked much more whitish. These looked considerably darker. And the packing also seems different. In fact, this is polypyrrole, this is polyaniline. Even there you can see some differences in the grain sizes and all, possibly. But what we basically do is, we make this hall bar kind of a structure, some kind of a hall bar structure like this, right? And then we basically pass current, pass current and measure a voltage by 4 probe. Just wrong. We have a lock-in, just pass current, measure voltage, and reverse it and do all kinds of things. And doing that, this is what is interesting is, you actually see some kind of a optimum sort of concentration of the SOMs and the pyrrole and aniline. So in aniline there's a very clear peak. For pyrrole it's not that clear. It basically, so what happens, of course, the conductivity is changing, most likely because you have a co-deposition of the molybdate and the pyrrole. So what we are doing here is we are changing the molybdate concentration. So if you have too much of molybdate, of course the concentration of the pyrrole would fall. The conductivity of the whole thing would fall. But if you have too little, you probably don't have enough to form good tracks, because the tracks are mostly happening because of the SOM itself. And the SOM also is acting like a Lewis acid, as Shomo said. So it has some kind of effect in the entire conductivity process. So for example, if I just start with pyrrole, I cannot form any tracks, right? With aniline, I cannot form any tracks. If I have to put the right amount of SOM so that I have a track which is robust and which has enough of electrons, free electrons and all, so that I can get some conductivity. So this is again, this is a data. So analysis probably can be done. Chirus can have a look at this. But this is data. This is very clearly showing this is happening, and the conductivity that we measure is theoretically, experimentally, this is on the highest sides. So what we have seen is some papers have kind of said that it is possible to achieve this amount of conductivity, but they have not really reported something like whatever 500 and 700 that we report here. It's pretty high. But the beauty of the process is you're making the whole thing in situ. You're not taking polypyrrole and making circuits. You're taking pyrrole, you're producing polypyrrole, and you're drawing a pattern almost in seconds, right? And in principle, you can make devices out of this. That is the next step. That is the next step. We probably can take 2 different materials and try to sort of do this Z-stack, and then try to make even transistors or something. That is the next step. Take different kind of materials and do this. But the whole beauty of this is the efficacy. It's so quick and it's so easy to do. Of course, controlling the amount of, if you take different sort of heterogeneous things and all, then I don't know what will creep in where. That I don't have, but I don't know really at the moment. But possibilities exist, I think, which can be really explored, because you can make this kind of printable electronics so quickly and so easily. Okay. So there goes that. That is the end of my talk there. So now I would say something which is which we really like, and that is the next aspect, that is having the probes, having the bubbles as probes for flows. And this is where we have sort of a lot of things that we want to develop again in the future. At the moment we have some stuff which we have tried to explain by a very empirical model, which I will absolutely admit at the onset itself, but which is matching the experimental data quite well. Let us start. So first thing that I would like you to concentrate upon is that these bubbles, while they are not directly trapped by the laser beam, by the Gaussianness of the beam, are however trapped much more robustly than you have normal polystyrene or whatever, normal dielectrics or nanoparticles or optical tweezers, much more robust. And why? Because this is an experiment that we did where I took the bubble, right, and I manipulated the laser beam. In the sense, I gave a ramp or a sine wave or something like that, so that the bubble sort of just, I modulated the laser. And look at the frequency of modulation. I modulated by 5 kilohertz. So 10 kilohertz basically means that suppose I took a polystyrene bead which is trapped at a stiffness corner frequency of maximum you achieve is say 1 kilohertz or something like that. But typically what this means is if I, for example, have a bead which is trapped at say 200 hertz corner frequency, if I modulate at faster, then the bead will not even see the laser change. Because when the bubble moves with the laser, basically means that the laser is trapping and pulling it, right? So then the bubble is continuously trapped even when I move the laser that fast. If my trap is like weaker, as is generally the case, if you move it that fast at 5 or 10 kilohertz, you will just it's for the trapped object. It is basically, it will average out to the beam not being moving at all. It will move so fast. The beam it will remain trapped. In fact, that is how people trap using pulsed lasers. Debu Goswami at IIT Kanpur, he sort of published a lot of papers on pulse trapping. It's because of that, because the beam is like, it is on and off, but it is on and off so fast that the bead doesn't see it. Right? And obviously pulse lasers are very high energy, so you need very little powers. So here what we saw is you can actually, so what I had is a detection beam which is fixed. The detection beam is fixed and I move the bubble. So the detection beam sees the bubble twice in one cycle, once when it goes like that and once when it comes back. And the spacing between these is the frequency of movement. And I can do a very quick easy calculation. I can see that it stops responding at around 10 kilohertz where you cannot see the bubble move. The oscillation frequency keeps on reducing actually, it doesn't go beyond that. So it's very easy to calculate that the trapping force is around 2 nanonewtons, which is almost straight an order of magnitude higher than what is achieved in normal optical trapping with dipole forces. Right? So this is really robustly trapped. Okay, so now this bubble growth, what really gave us a very nice idea about the flow fields around the bubble is just studying the growth of the bubble with the laser power. As easy an experiment as that, very simple, but the analysis proved to be very, very tough, very non-trivial, because what we are having here is what I said is homogeneous nucleation, which is basically, so typically normal boiling in water happens because you have these heterogeneous nucleation sites, and so you have bubbles because of that. Basically that, heterogeneous nucleation. Same thing as rainfall or all that, right? So here, however, you have a very small area which is suddenly given a thermal shock and the water essentially gets superheated. And if that continues, then basically the phase of water would cross the spinodal limit, where water ceases to be a liquid, surface tension goes to 0, conductivity is infinite. So just to stop that, you have a bubble which forms. Right? And now the size of the bubble with laser power is actually a beautiful, elucidates just the environment of the bubble, because the moment the bubble is born, you have immediately flows around it. And that is basically checking or acting as some kind of a very crucial factor of the flow of heat as well. That is what we found out. Right? So what we actually found here is we are able to go towards that critical temperature of water where the water approaches that spinodal limit, which sort of exposes a phase explosion. We are able to approach that. And how? That's what I'm going to show you. So first what we did was we just increased the bubble. We had a bubble formed at a particular laser power, just waited. What we saw was within few seconds, 10 seconds, the bubble reached a constant size. So realize this, you are actually continuously putting in heat, right? Because the laser beam is on, but the bubble does not expand. And that actually is happening because of the SOMs, because these SOMs go and create that ring. right? There's a ring around in that base. So basically the water cannot approach that hot spot. The hottest spot is on the glass slide, right? That is where I focus the laser, and I have a ring of material around it all the time. The moment I have the bubble formed, initially there is nothing, but then instantaneously you have this kind of convective flows which draws in material, which forms a disk, and that sort of stops, that increases as the bubble stays. Material keeps on accumulating, and that basically stops the flow of water. So you have lesser and lesser water which approaches the hot spot. As a result, the bubble sort of gets static. It almost reaches an equilibrium position. Of course, convection also plays a big role, as I'm going to show you, right? But what is very crucial for the experiments is that we could actually get an equilibrium size of the bubbles at different laser power. This does not happen, for example, when we use a gold substrate. If you have a gold substrate, we see the same thing. We have a bubble, but it keeps on growing, just keeps on growing. That is a different thing. I'm not covering that today. That's also quite interesting, that there's a power law. There's a power law which is quite interesting. But so what happens was, so we did basically,
I'm not sure I understood why the ring is forming.
the ring is forming because material is coming in, right? So you have, so basically just think of this, Sharat. You have the bubble like that, right? So material is coming is at the edges. So the imprint of the bubble is a circle, right? So material can deposit only there because the bubble otherwise is in touch with the top slide. It is pressed against the top slide. So the material basically comes in from the edges. Yes. So there is an inward flow, right? In the radial direction there is an inward flow, and also there is an outward flow in the z. So it is coming like that, like this, right? So as I will show you, when we just image in the radial direction, you just see particles coming like that. Of course, z we cannot image without confocal, right? So if the effect of the z, that the fact that the z is actually happening is the ring, because your particles coming like that. It thickens with time. That is what I'm saying. It thickens with time and it prevents water from coming in at the hot spot, right? So we basically did 2 experiments. So the first experiment was, sorry.
How do you say this flow? Like, how do you see the flow?
See the flow.
You're seeing that-
No, we'll come to that. Have a bit of patience. Yeah. So this first experiment was simple. I have one bubble. I keep on increasing the laser power, and what I see is this nice linear thing. Oh shit! I did not group that. Sorry. Forget about this. So this is where I just see a linear growth of the bubble size. Easy. Just one bubble. I form it at the laser power. Bubble comes. Increase the laser power. Bubble size increases. The second one is what is really interesting. This is a second thing where I have a bubble formed at a particular laser power. I switch off the laser. Bubble disappears. Fresh bubble at a higher power. New bubble. Measure. Switch off. Another bubble. New power. New size. That has a completely different look. So it grows fast, saturates kind of, and then suddenly shoots up. And this completely perplexed us because we repeated this I'm just giving you one sample data. 5-6 times we repeated, n number of times, every time this happens. You suddenly increase at a slope which is sharper than this. Saturate, shot off suddenly. And here this is really, really sharp. And I can't go beyond this power because why? If I go beyond it, the bubble fills up my screen. I can't measure it. There's one huge bubble. I can't measure anymore because my imaging is also at 100x. If I change that, then everything changes, right? My spot also changes. So this is what we had to explain. And this is not simple at all, right? Because these are so qualitatively different kind of things. But it's very interesting. So what did we do? So we had to basically find out the temperature profile. This is my geometry. I have a hotspot, right? I have a bubble. I have flows like that. This is my, so xy is my radial, and xz, z is my axial. So it sort of goes and hits at the sort of, if I look at the xy plane, like it is, x and y are the same. It's like a r. It's basically r and z. There's symmetry in xy. So I can, 3D sort of reduces 2D. So I have this equation to solve, right? Where the crucial thing is there's a diffusive term and there's a convective term. This is ultimately important. The diffusive term and the convective term, right? And I can remember, I can image my experimental data can only be on certain xy planes. I can take slices and measure on different xy planes, where I will see an inward velocity, things coming in. Of course, they move in at the like here. So how do I? The problem is by this approach I can find the temperature profile, right? But just the temperature profile doesn't help. I need to find out the radius of the bubble from simulation at a particular temperature profile, at a particular temperature, right? I have an x, y, z distribution of temperature. At each z temperature, I need to find out the bubble size. How do I find out? Here I use the classical theory of nucleation, homogeneous nucleation, where they define a critical radius. So critical radius means a balance of this pressure delta P, 2R by delta P. That is basically the radius beyond which the bubble cannot grow. Because the pressure differences become negligible, you cannot grow. Right? So at each temperature, I can actually I find out the pressure from this Ottawa equation or whatever. Right? And from that, I can find out this. So basically that means that at every z slice, I find out the temperature, I find out the critical radius at that temperature and see whether that distance from the origin is greater than the critical radius or less than the critical radius. If it is greater than the critical radius, the bubble will grow. Right? So this probably will be clear in this graph. So this is my temperature profile. As z, this is distance from the hotspot in the z direction. I get a profile like this, right? And at each point I calculate the critical radius. As long as the critical radius is smaller than this distance, my bubble is growing. At one distance it will cut. Where it cuts, I define that to be my bubble size. Right? That much far from the origin, there is a certain temperature. If I plug in that temperature in that equation, I find the value of critical radius which is equal to that distance, which means that is the equilibrium distance of, radius of the bubble. That is the theory as we figured out from this. How does this grow, right? So then first we did only diffusion, because convection is tough. We threw away convection, just diffusion. And if you do just diffusion, this is what you get. Continuous increase of size of the bubble. Continuously it keeps on increasing, which is not what we see. Therefore, you basically cannot throw away this term. Why? Because of this. So just wait, there's a bubble and you can see. This is 1 micron beads. 1 micron beads which are coming and nicely hitting the bubble, which means these are classic convective flows. Right? Which essentially means I have to consider the convection term. Right? And that is, but then it is not so simple, because Vx I have to know some functional dependence. How on earth do I know? I can do it, of course. Ranajaya can solve the complete Navier-Stokes, which is completely non-trivial. We did not do that. We could not do that. So we found an empirical means of finding out V. And that I used by experimental data. So what we did is, as you saw in that thing, we had these 1 micron beads which come in. I measure for some 20-30 beads. I find out how they go with distance from the center. The nice thing is they follow 1 by r square as it goes away from the bubble, far from the bubble. But near the bubble it is not like 1 by r square. In fact, it is closer to this. It is much closer to a straight line. Right? This is all empirical, completely empirical, pardon me. But this is like a slope of this. And we need to know, however, what will be the thing at the surface of the bubble. That is, I will not be able to measure. Right? Very, very close to the bubble, because it's very fast there. So what I do is I take the intercept, the y-intercepts of this thing. And remember, my final thing is to find V as a function of temperature. And how do I find the temperature? The only means that I have to control temperature is the laser power. So somehow I can vary the power and I can get an equivalence of power to temperature and try to measure what is the velocity dependence at different temperatures. What is that intercept of that line at different temperatures, right? And that is what we do. So that intercept, so now so it's fit in very beautifully actually. So from that critical radius diagram that we saw that the critical radius intersects at a temperature where at the axial distribution of temperature at around 110 degrees. So after that the critical radius would be more, so you would not have a bubble. So it means my threshold, my bubble surface, the theory tells me it's at around 110 degrees, right? And we have seen, I showed you that threshold power, you must have noted it, that was about 16 milliwatts. So it means 16 milliwatts is increasing the thing to 110 degrees, right, something like that. If I assume that, and if I say that my maximum power that I saw was about 70 milliwatts, then if I just assume a very simple linear relationship, I will get that this 70 minus 16, 54 milliwatts, that kind of, I can just say that if 16 milliwatts increases by 110, how much does 54 increase? Very simple. And that comes to 644 Kelvin. Okay, you understand, right? 16 milliwatts correspond to this much of temperature rise. Therefore, 70 milliwatts correspond to how much? And you add it with 273, of course. And you will get something like 644, which is basically the critical temperature of water. Okay, this was something which we had no clue about this critical temperature and all unless we read up all these things. We saw that it matched. So we had some kind of an inkling about how the temperature and the power can be sort of related. Obviously, it's a very simple dependence. Okay, and then what we saw was this is the threshold, that is that, not threshold, this is that intercept of that line, straight line at different laser powers. And we saw that you could fit either a straight line or this thing, polynomial of root 2, right, square. Even both fit, because see, I don't have really theory to guide me here. This is empirical. So I took both. I took a linear, I took quadratic, both. And my aim was just to see what would fit the data better, because finally the data speaks, right. So I have some dependence of the velocity, convective flow velocity, with temperature now. T threshold is my temperature at which the bubble forms, and T is my hotspot temperature, right. And that I see TH is the hotspot and TTH is the, oh shit, sorry, and this is very nice. So now once I plug in that, I already see that the flow is arrested. I mean the growth is arrested. The bubble size has already been arrested. But remember one very critical thing. I am measuring this with a bubble that is already there. Whereas what I am modeling is the situation before the bubble. Right? I had put in the hotspot, there is a temperature distribution immediately which puts in, which is at faster timescales than the bubble growth, much faster. So obviously I have to put in some factor here, because this is before the bubble. And obviously the surface tension dependencies will be less, so the convective velocities would probably be much lesser, because I don't have a bubble then, I just have a temperature gradient. So I have to put some fudge factor A, some fitting factor A, I don't know that. That is what I determine from my fitting. And you can see that it indeed matches really well. What is nice is when I have only diffusion, straight, nothing, there is nothing, there is no plateau, nothing at all. If I keep this A2 less, it does not fit. I do have a fit parameter which actually comes quite close to the data. So this is, so, and why does it shoot up suddenly here? Because I assume that D, that is diffusivity, I take it as a function of temperature. At 644 K, diffusivity explodes. And obviously in the heat equation, then this term would dominate completely, is D. This would explode and you would basically get a sudden rise in the thing. Right? This is nice actually. So now there is another very beautiful thing which comes. We had the first case where it was a linear growth, and now we have this case where this is like this. How can we compare the two? Can we at all? Are these two different things? They are not. Because remember in the first case, you have a bubble which had air inside, right? So obviously the heat dissipation is much higher. Whereas the second case, I am creating new bubbles all the time, and then I have water, right? So obviously when I increase the temperature in the first case, where for a single bubble, I just have a temperature at the hotspot, I have a temperature at the surface of the bubble, at the bottom surface. So obviously there are flows. Obviously there is convection happening. And the proof of that is I see that the slope here and the slope here are almost same, within 30%, 20-30%, whereas here this is a factor of 3. So for the single bubble case, it is very clear that we have convective flows which essentially dominate the increase of the bubble radius. Whereas when I do this thing of shining the laser at different powers, creating different bubbles, I go through all the domains. Here diffusion dominates when the bubble is very small, because the temperatures at the hotspot and the bubble surface are much lower. The hotspot temperature is lower, delta T is smaller for small bubbles. When I increase the hotspot temperature, convection comes in and it arrests the flow of the growth of the bubble. And finally, when I approach that hotspot temperature to be at 644, for the second case I do have an explosion, because remember there was water there. When I turn on the laser, the hotspot goes straight at 644, it is water, the water shoots up. Whereas for the first case I have air inside and the water does not even touch the hotspot because there is a ring also. So I barely approach the hotspot. Of course, if I have a very powerful laser, very high power, I probably can go to extremely high powers and force the conductivity of air also, to sort of, the critical temperature signatures to come in for water. Right? So this is very cool actually. So we could actually see this happening. So this is basically what we did again, homogeneous nucleation. We saw that we could actually mark the regimes of diffusive, heat diffusion and convection, and also this phase explosion in water. And this was probably a direct observation of that, which is pretty nice. We've just sent it. Let's see what the referees say. So finally, what I'll just show you is some, as I said, some nice dynamics that we do with flows. So you have two bubbles here. You have two bubbles here, and this is what we were discussing with Pramod the other day. So we have two bubbles here, and I just let them be, and I see these particles coming. So there's some particles on the top, some particles on the bottom, and this basically happens, the simulation Ronojoy did. So essentially what we have is some kind of separatrix here, right? So particles above this separatrix come here, below this come there, right? So basically I can kind of modulate the flows in such a way that the particles could reach either bubble. What is interesting is, what we plan to do is, if somehow we can make this separatrix fuzzy, that is, if I can actually modulate the bubbles, then probably I will get this thing to modulate. If this modulates, there is a possibility that there will be some which will go through, right? Because if a particle tries to go this side, this bubble expands. It goes to go this side, this bubble expands. If it tries to go that side, this bubble expands, and the particle can, in principle, go through. So this is something which we plan. Some other cool stuff is that this is particles loaded on the bubble, and I can nicely translate it. This is something where we carry gold particles. This is contrast is very bad. I don't know whether you can see this is gold which we are picking up, but this is stuff which people have reported before. We are reporting something nice where we can actually have bubbles, particles loaded, and we can release them. See, I am pulsing the bubble, and particles are getting released. So, right? So in what people have, I think Hema has shown, Hema and Deepak Mathur has shown, that they use bubbles as scavengers of nanotubes or something. So what we can show is that we can of course load particles and go about, but we can actually catch particles and also release them sort of completely controllably by just pulsing the bubble. You can see that this particle goes out, and of course it comes back because I don't move the bubble away. If I move the bubble away, the particle will just get out and stay, right? And this is another thing, this is nice, some self-assembly that we see, that we have just explained again with the help of Ronojoy's modeling, that basically this kind of nice assembly that we see on the bubble surface, essentially just because the flow lines converge on an equilateral circle of the bubble, which I think Rajesh showed in this one bubble simulation here. Yeah, so that is what, I think I'll stop here. Right, so what we have shown is that we have lots of applications. Some, I hope I have convinced you that you can do a bit of magic with microbubbles. You can make nice patterns. You can actually investigate things like the critical phase explosion in water, and of course you can modify fluid flows in such a way that particles can be manipulated in a way that optical traps cannot do so simply. I mean, you're actually manipulating the flow without trapping them. And especially we want to work on the multiple bubble geometries and see if we can achieve exotic things. Right, so yeah, thanks.
So you have shown us that the velocity of in a particular plane, like a particular z value, where you show the velocity is inward. But you are talking about another flow where you say that the yz plane, right? So that, how do you know that there is a velocity in the yz plane? But
The assembly of the particles, right? That they have particles assembled at the base of the
but
bubble,
we
which
have
tells
not-
you that there are
do you have any
things.
mechanism to see that, whether you can
That
see
is
the
very
velocity
non-trivial,
of it?
because you basically, you see, when you imagine an optical trap, you just see the radial,
that's why
right?
I'm
So
telling you, yeah.
Y stacking, Z stacking, you have to have confocal tweezers or something where you continuously image. It's possible by tracing particles, but then this is a standard theory, so there is no reason to believe that it will not happen actually. Because you have anyway those ring formation, right, which tells you that there are particles obviously coming in from the bottom, actually.
Thank you.
Yeah.
So you made a comment that when you had a gold substrate,
You
your bubble kind of grew.
keep
without
on,
any
keeps
limit.
on, exactly.
What's the difference in the mechanism there?
No, difference, but there is nothing to stop it, right? Because here we don't have the ring. Here, so normally it would
So
keep
there
on
you
growing.
won't use the song.
No, of course not. No, of course not.
It just keeps
It just keeps on growing. So there what we do is we make some scratches on the top so that you have these local plasmon effects, right? So that causes the absorption. So that causes absorption and you get a bubble coming, but that just keeps on growing. So you cannot define an equilibrium radius. So that power law is actually very fascinating. So we get a t to the power 1/3, which is not reported. So we are trying to solve for that, why we get that t to the 1/3.
So you are hitting it from the top, right?
No, bottom. We are hitting it from the bottom to the top. So the sample chamber is like this, I am coming from the bottom to the top.
So it's convectively unstable.
Right.
Any other questions? Any questions?
Okay, thanks.
Okay.
Thanks so much.
Fine. If there are no further questions, no, there is.
Sharat, of course.
So I'll send you a video, but we tried this, I think I was talking to you.
Assembly,
We tried this with,
bacteria.
with bacteria, and you see that there are these annular rings.
Well, it's the same thing, just because of that.
Well, it's also, they are light bacteria.
But they are active matter, so that makes it much more complicated, right?
But do they survive the heating?
Not the ones at the very
Closest.
center of the bubble, but the peripheral ones.
But you know, that is an issue. That is really an issue. I mean, these biological things not withstanding temperature is very bad. So see, because we have some ideas of even making chips which are like, you know, these patterns of proteins. You can do that, it's nothing, because finally whatever is there will be patterned. Only thing is, I don't know if proteins will survive that. Even that small time of this high temperature that we sort of, you know, expose them to, because this is very small. In fact, see, pyrrole and all, they don't survive, polypyrrole will not exist at that high temperatures. But then the thing is that we move it away so quickly, there's a sudden flash and then it stabilizes immediately. So that, and obviously polypyrrole we are creating because it is conducting. By the way, I didn't tell you one thing. So SOMs, just the bare SOMs, when we measure the conductivity, it is in mega ohms and all. So at least doesn't tell us that Shubhra was fudging data or something. At least that's what he told me. So I believe that SOMs are actually quite not conductive actually.
Okay. If there are no further questions, let's thank Ayan once again.
Okay.